Heureux d'un printemps qui me chauffe la couenne, triste d'avoir manqué encore un hiver. Je peux pas faire autrement, ça me fait de la peine. On vit rien qu'au printemps dure pas longtemps. Après d'aller, assis sur le bord de mon taureau, je me creuse la tête. Je pense au bonheur des gens, je sais bien que ça va pas durer. Ça prend des sous pour faire la fête. À qui appartient le beau temps, l'hiver, l'été durant. L'été c'est tellement bon quand t'as la chance d'avoir assez d'argent pour voyager sans t'inquiéter. Pour le fils de patron, c'est les vacances. Pour la fille du restaurant, c'est les sueurs et les clients. Après on dit que l'hiver est blanc comme un nuage, mais ça évidemment dans le chalet près du foyer. Dans le fond, c'est salissant pour risquer le chauffage. Le pas pire au moment de l'année, quand il est pourtant d'été. Après
hopefully over the weekend for the midterm marks.
Faut que je monte dans mon taureau, creuser ma peine. J'ai vu le surintendant, je peux rien dire en attendant. Le jour où ça sera nous qui feront la fête. Imaginez le printemps quand l'hiver sera vraiment blanc. Qui chauffe la couette, triste d'avoir manqué encore un hiver. On va faire autrement, ça me fait de la peine. On vient pas printemps dure pas longtemps. Dans le printemps, qui chauffe la couette, triste d'avoir manqué encore un hiver. On va faire autrement, ça me fait de la peine. On vient pas printemps dure pas longtemps.
All right, how are we doing? No need to worry about rotating about lines that are not parallel to the X or Y axes. We're not going to focus on that. Sean was asking about, well, let's do this one first and then we'll do Sean's question. Today we're going to do arc length and surface area. Time permitting, of course. Certainly arc length. Hopefully surface area as well. Let's consider this. So first, a few things, right? From now on, you have to always ask yourself, do I have an improper integral? Of course, you have an improper integral here because you have an infinite domain. But if you look at the denominator here, your function blows up if the denominator is 0. In other words, at plus or minus 2. Luckily for us, these are not included in the domain. Had they been, you would have had to break it up appropriately. but not an issue here. Today's music brought to you by Paul Pichet, a Quebec artist. Really embodies the Quebec French sound. A lot of newer bands have adopted his sound. Never had a huge hit. I mean, I think this is his best known piece, but has a nice cult following. I mean, more than a cult following. I think everybody enjoys and respects him as an artist. I can look that up. Thought it would be appropriate as it's supposed to be 12 and sunny today. All right, back to this. So you know what to do, right? Improper integral. This is really the limit as n goes to negative infinity of the integral from n to negative 3. This transforms an improper integral into a regular integral, and then you just take a limit. That's really the definition. Integration is trivial here. You can do that in your head. On an exam, of course, you want to show all the work. Simple U substitution does the trick here. And we get negative 1/2. And you see what happens, right? As n goes to negative infinity, this goes to positive infinity. 4 minus infinity is negative infinity. Absolute value, which is infinity. Log of infinity is infinity. And we are done. The integral diverges. Questions? Let's consider Sean's question. I'm going to go 1 to infinity. 1 over x squared plus x. How do we know when an integral diverges versus converges? If you get a number, it converges. Anything else diverges. Isn't it ln of negative 5? Well, we have absolute values there, right? Absolute values. You're missing absolute values, Paul. You'll recall that the integral of 1 over x is ln of absolute value. So again, 2 things. Improper integral, yes, because of the infinite domain. And this factors, let's take it a step further. This factors is x times x plus 1. And the denominator is 0 when x is 0 or negative 1. So again, you're going to want to ask yourself, does the function blow up in the interval, and in this case it does not, right? It blows up at 0 and -1, which is not in the domain. So this is improper because of the infinite domain. And now the question is, how do we integrate this? Well, you know exactly how to integrate that. This is a rational function where the degree of the numerator is less than the degree of the denominator. So, partial fraction decomposition. I'll let you do that, but I think it's clear that this is 1 over x minus 1 over x plus 1. Again, show all work when you do this. Decompose it as you know you need to. Let's finish it over here. So decompose it and solve for the variables, but there's the result. And this is just ln of x minus ln of x plus 1 from 1 to n. And this is ln of n minus ln of n plus 1 minus ln of 1, which is 0, minus ln 2. And now as n goes to infinity, here you have infinity minus infinity. In a limit, you know that to be indeterminate. Something's got to be done. What are we going to do? Well, luckily we're dealing with lns. So we can rewrite this as ln of n over n plus 1. And as n goes to infinity, n over n plus 1 goes to 1. A simple L'Hopital's rule, or factoring out an n from the denominator, will give you that. So this goes to 1, and ln of 1 is 0. So the whole thing is ln 2. How are we doing here? Questions? How are we doing with improper integrals here? Can we take ln out of the limit? You can take the ln 2 out of the limit for sure, but not these lns, right? Why is the n inside the integral equal to 1? It's not the n that's equal to 1, it's the n over n plus 1. The limit, as n goes to infinity, of n over n plus 1, this has the form infinity over infinity. A quick L'Hopital's rule. Quick L'Hopital's rule will give you 1 over 1, which is 1. So it's not the n that's 1, but the expression n over n plus 1 goes to 1 as n goes to infinity, and ln of 1 is 0. Perhaps, Amir, what you were asking is, can you take ln from here, take it outside and just take limit of the inside. And you can do that. Exactly, right? So that's exactly what Amir was saying. And why can you do that? Why is the limit of the lawn equal to ln of the limit? Somebody want to address that? Right, so exactly, thank you, Shamir. Because, and Amir, because ln is continuous. Very nice. That's exactly why. Let's consider the comparison test. Suppose you have a function. Well, I mean, suppose you've got two functions, f of x and g of x, which are, first of all, bigger than 0, and secondly, related in this way where g is bigger than or equal to f. If the integral of g of x converges, then the integral of f of x converges. And 2, if the integral of f of x diverges, then the integral of g of x diverges. Let's prove that, because the proof is trivial. The proof is trivial. It's just one line. You have this inequality already. So the integral follows the same inequality. And similarly, the limit follows the same inequality. Right, this is one of the properties of limits. Right, this was one of the properties of integrals, and here we have one of the properties of limits. In other words, what are we saying? the integral from a to infinity of f of x is less than or equal to the integral from a to infinity of g of x. Yeah, kind of like the squeeze theorem, kind of, but the right-hand side and 0 don't have to agree, right? The limit of the right does not have to be 0. But look at what happens. If this integral converges, if this is equal to a number, if it's equal to a number, then it's going to be strictly less than infinity. And consequently, the integral here is going to be strictly less than infinity, and so it will converge. Conversely, if this integral diverges, in other words, if it's equal to infinity, then this integral will be bigger than or equal to infinity. And so it will have to be infinity, it will have to diverge. There it is. In other words, if the bigger one converges, the smaller one converges. And if the smaller one diverges, then the bigger one diverges as well. All right, consider this. You'll notice that we are integrating over a finite region. So it's not an improper integral in the sense that we're integrating over an infinite region, but I'm sure you've recognized that the function blows up at 2. Right? When w is 2, you have 2 over 0, you have some sort of infinity. So we're going to break this up as the integral from 0 to 2 plus the integral from 2 to 5. And as we suggested, as soon as one integral is infinity, that's it. So let's concentrate on one integral. Right, this is improper because of the 2. So this is going to be the limit as b goes to 2 from the left of the integral from 0 to b. For the rules on the comparison test, do they work in reverse? Also, what do you mean by reverse there, Brandon? It's not an if and only if statement, right? In other words, if this diverges, it doesn't give us any information on the smaller one. The smaller one may converge or may diverge. We don't know. And similarly, if the smaller one converges, this does not give us any information on the bigger one. The bigger one may converge or may diverge. What page is this example from? 549. now you know how to integrate this, right? You could make a u substitution, u equals w minus 2. Works nicely. Long division, because they are of the same degree. Or let me add a 2 and add a 0, really, right? Minus 2 plus 2, which is the same as long division. And this is 1 plus 2 over w minus 2. If you do long division, this is what you're going to get. So integrate, integration is trivial here. W plus 2 ln of w minus 2 from 0 to b. And subtract, plugging in 0, so minus 2 ln. And as b goes to 2 from the left, this goes to 0, to 2. But as b goes to 2 from the left, this goes to 0, and ln of 0 is negative infinity. So the whole thing is negative infinity, i.e. the integral diverges. And there's no need to consider the other one. Again, we're not going to say, well, this might go to negative infinity, but if this one goes to positive infinity, don't they cancel out? There's none of that. This integral diverges, so the whole thing diverges. Amir is asking, isn't it ln of a negative number? But again, absolute values. Don't forget your absolute values. Ashley is asking, by smaller and larger, do we compare based on the bounds? Did you mean in the comparison test? If you mean in the comparison test, it's not based on the bounds, but on the whole interval. Your function has to be larger than the other one on the whole interval. Would we say the whole integral does not exist? Yes. Or diverges. Is the infinities canceling out something we would look at in more advanced classes? Short answer, no. Longer answer, yes, in a different context. As I suggested last time, there is something called the Cauchy principal value. Which finds its way naturally in the study of complex numbers. So if you take a course in complex variables, you would use that. Yes. Isn't it positive infinity because of the absolute value? It's not the ln that is in absolute value, but rather this business. So as b goes to 2 from the left, this is going to go to 0, right? And ln of 0 is negative infinity. Well, I mean, ln of 0 does not exist, right? But as x goes to 0, ln of absolute value of x goes to negative infinity. So, you know, in a different course, you may see the Cauchy principal value, but it doesn't take away from the fact that the way we defined it, this integral diverges. The Cauchy principal value may give you a different answer, but that answer will be for the Cauchy principal value, not for the integral itself. Why do we want to split up the integral? Because we noticed, I mean, I've erased it now. Let's rewrite it here. We noticed that the function blew up, the integrand became infinite when w was 2. And 2 was in the interval. Right, so it's important. So this is an improper integral because your function blows up. Amir is suggesting because of symmetry, a lot of stuff cancels out, but it doesn't cancel out because it's actually infinite. That's the thing. That's the issue. Well, if it wasn't in the interval, then it would not be an improper integral, and there would be no need to split it up, right? If it's the integral from 5 to 7, no problem, just integrate as usual. It's not an improper integral. But here it is improper because 2 is in the domain. And let's consider this example. Right, this is an improper integral because you're integrating over an infinite region, but also the function blows up at 0. So it's an improper integral of those two types. Infinite domain, but also function becomes infinite in the domain. So immediately we'll break it up into two pieces. It doesn't have to be at 1. It can be anywhere you want in the domain. 2, 3, 4. That's not going to affect the answer. I broke it up at 1 for convenience, but there it is. Now you have two separate improper integrals. This is improper because you're doing it over an infinite region. This is improper because your function blows up at 0. We're going to treat both integrals separately and see what happens. So again, this first one is improper because it blows up at 0. So this is the limit as a goes to 0 from the right. This is just 2 root x. And this is 2 minus 2 root a. And as a goes to 0, this is easily seen to be just 2. So first integral converges to 2. Excellent. Let's move on to the second one. Second integral. Improper, not because your function blows up, right? It only blows up at 0, and that was in the first one, but because it's an infinite domain. Same antiderivative, there's no surprise there. And as n goes to infinity, this goes to infinity. Square root of infinity is infinity. The whole thing is infinity. The whole thing diverges. So this one converges, but this one diverges. The whole thing diverges. Effie, there's an excellent reason for that. Effie is asking, in this question, we had the limit as b goes to 2 from the left, whereas here we have the limit as a goes to 0 from the right. Why is that? Here, our domain is 0, 1. Our domain is 0, 1. In order to stay in the domain, the only way you can get to 0 is from the right. Over there, we have the interval 0 to 2, and we wanted to get to 2 while staying in the domain. The only way we can do that is from the left. So you want to stay in your domain. That's what we're doing here, right? The idea, again, if you recall what we're really doing, we have the intervals from 0 to 1. This is going to look something like that, right? It blows up at 0, and we're breaking it up at A, calculating this area and looking at the limit as A goes to 0. Absolutely right. Notice that the 1 doesn't really matter here, right? Whether it's 1 or 10. This would have been 2 root 10. And this would have been a 10 here. And it's not the 10 that plays a role. It's the 0. It's the A and the N. The place where you break it up really does not play a role. And notice, in fact, when you add the two together, right, you would have added this answer and that answer, and they would have canceled out anyways. But even if they did, even if both converged, they would have canceled out. So the final answer is that everything diverges. Absolutely. And Sophia is asking, why does the whole diverge? Well, I mean, one answer is finite and the other answer is infinite. So when you add them together, you're going to get infinity. Diverges. Why is it useful to know if the area under functions converge or diverge? Well, as suggested, the idea of convergence implies that your function is going to zero fast enough. This is going to be very, very, very important next week when we talk about series. And we'll see a beautiful relationship between series and integrals. So right now, not really clear why we care that much, but I mean, it's a question that comes up naturally, right? I mean, in terms of limits, what is happening to this area? Is it going off to infinity? Even though you have an infinite region, right? You have an infinite region, it's still possible to get a finite area. Riemann sum is considered a form of series, but usually the term series is reserved for something else, because series, as you'll see, are usually infinite, whereas Riemann sums are finite. I mean, you do take a limit of a Riemann sum, so that kind of becomes infinite in that sense, but we'll see. As Harry suggests here, this will converge for p bigger than 1, and let's work that out. First of all, improper because you have an infinite domain, but the function might blow up. And what happens? The function blows up if x is 0, but 0 is not in this domain. So improper only because of the infinite domain. So this is going to be the limit as n goes to infinity of 1 to n. There it is. Now the question is, what is the antiderivative of this? And as Ananya suggests, the antiderivative is going to be different for different values of p. Katrina, March 9th, recording has been restricted on YouTube because of the opening song. I've posted it on my courses, so you can find it on my courses. Converge does not mean equal to infinity. Converge means the limit is a finite number. And Kenza, same answer for you, right? So Ananya suggested that when p is negative, when p is -1, well, actually when p is 1, this integral is different from all the others. So we're going to break this up at p equals 1 and see what happens, right? Because you know when p is 1, you get a ln happening here. Yep, exactly. Copyright infringement. That was the deal. Well, I mean, it's all good. You know, they're protecting themselves. No worries. Yeah. Right? It is what it is. At least they allowed me to download it and offer it on another platform. I am certainly not making any money off these streams there. Right, so what's the conclusion here? The conclusion is that if P is equal to 1, the integral diverges. Yeah. I am making a salary, so it's all good. I mean, look, yeah. All right, so let's get back to this. If P is equal to 1, integral diverges. What happens if P is less than 1? If P is less than 1, I claim one over x to the P is going to be bigger than 1 over x. How is GME doing this morning? Ahmed? Right, why is that? Is that true? If P is less than 1, let's cross multiply. Right, we'll multiply the whole equation by x. And what do we get? We get x over x to the P. This should be greater than 1. But this is really x to the 1 minus P. And 1 minus P from here, if you bring the P to the other side, 1 minus P is bigger than 0. So x to a positive power is going to be bigger than 1 because you're on the interval 1 to infinity. All right. Yeah, I should have bought a 40, seriously. I mean, I still have the 1 stock. Just for fun, but I mean, now I'm making money, but should have bought a few at 40. This is not financial advice. Right, so you see that on the interval 1 to infinity, 1 over x to the P is bigger than 1 over x if P is less than 1. Well, less than or equal to doesn't matter, right? And this was bigger than 0. Thank you. Yes. Thank you, Harry. Well, yeah, right. I mean, I figure, you know, they're talking about 10,000, 100,000. So I said, you know, look, I'll buy 1 stock. If it goes up to 10,000, I don't expect it to, but I was wrong with Bitcoin. So, all right, there it is. So by the comparison, test, since the small one diverges, the large one diverges. If P is less than 1. Good for you, Haroon. Nicely done. How high is Dogecoin? Dogecoin. It was, last time I checked, it was it 5 cents? Where is it now? So this diverges if P is 1 and if P is less than 1. What about too dumb or too smart? Right? Still 5 cents. Yeah. What if P is bigger than 1? We still have to answer that question. But if P is bigger than 1, again, improper for the obvious reasons. You know, here we didn't integrate, but you could have integrated. You could have integrated, it doesn't matter. You know, we did it with the comparison test, but you could have integrated in the same way that we're going to integrate here. What is the antiderivative of this? You know what the antiderivative is. That this is really x to the negative p. So the antiderivative is 1 over negative p plus 1, x to the negative p plus 1. Right, that's what the antiderivative is. And if you plug in 1 over negative p plus 1, n to the negative p plus 1 minus 1 over negative p plus 1. So the question is, what is happening to this business? What is the limit as n goes to infinity of this? So that's all that matters, right? But we're saying p is bigger than 1. So if you bring the p to the other side, negative p plus 1 is less than 0. I'm just saying that this is really x to the negative p. So that it's easy to integrate. Second line on the right side. This one here, this was to show, this was to prove this inequality. Absolutely, absolutely. If you integrated, you would have the same thing for p less than 0. Absolutely. Or well, in fact, for p less than 1. For p less than 1, exactly. So you could do this way just by integrating as well. Absolutely. What I want to point out is that in this case, minus p plus 1 is less than 0, as opposed to here. In this case, if you bring the p to the other side, minus p plus 1 would be bigger than 0. You could, absolutely. But I mean, it might be difficult to see. So here, minus p plus 1 is less than 0, so this is a negative exponent. So it's really a 1 over. Right, that's the key here. This is 1 over n to the p minus 1. right? Since this is a negative exponent, it's really a 1 over. And so the n is in the denominator. So as n goes to infinity, this goes to 0. And the whole thing converges to 1 over minus p plus 1. In this case, minus p plus 1 is bigger than 0. So this is a positive exponent. And as n goes to infinity, the whole thing goes to infinity. So you'd still have to break it up at this stage. But yes, you could do it in one step. So conclusion, the integral converges for p bigger than 1 and diverges otherwise. It is, thank you. Thank you, Ashlyn. I was missing a negative here, right, because it is negative. All right, how are we doing here? Questions? Let's move on. Let's move on to arc length. Here's the natural question. Suppose you have a curve. How long is it? If you were to put a piece of string on this curve and then straighten it out and measure it, how long would it be? That's the idea of arc length. Well, let's approximate it. You know, we like to approximate things. We're going to approximate it with straight lines. It's easy to measure a straight line. Right? Just straight lines. And these straight lines can be viewed as the hypotenuse of a right angle triangle. What is this for? Arc length. We're asking the question, how long is this line? How long is that curve? New topic. Right? So these straight lines are actually the hypotenuse of right angle triangles. I don't want to draw it for that one, but you see what's happening. Where this base is actually the change in x. And this height is the change in y. So, by the Pythagorean theorem, the hypotenuse is the square root of delta x squared plus delta y squared. And so an approximation to the arc length, we're going to add those hypotenuse. And that's going to give us an approximation to the arc length. Now, this is not a Riemann sum, right? Because a Riemann sum, you've got a delta x outside. So let's transform it by factoring out the delta x all squared from inside the square root. And we get a 1 plus delta y squared over delta x squared. And now square root of delta x squared, right? Square root of a product is the product of the square roots. So 1 plus delta y over delta x all squared times the delta x outside. And now you have a Riemann sum. As delta x gets smaller and smaller, this gets closer and closer to sum becomes an integral. Square root 1 plus delta y over delta x becomes dy dx. There it is. This is your arc length formula. Let me point out, right? So dy dx, the derivative. That's not what I wanted to point out, but right? So 1 plus the derivative squared, well, the integral of the square root. What I want to point out is, instead of factoring out a delta x, what if we factored out a delta y? Right, in the same fashion, you get a similar result, but with a delta y outside, and this is still a Riemann sum. And as delta y gets smaller and smaller, sum becomes an integral. This is 1 plus dx dy all squared dy. So you see you have two different formulas for the arc length, depending on whether you want to integrate with respect to x or with respect to y. Both must give you the same answer. Let's rewrite those formulas here. So the arc length, 1 plus dy dx, or 1 plus dx dy. Will this be in the web work? I'm sure it will at some point. I'll probably open up a web work right after class. I should do that. I think we have 6 wet work total. Doesn't matter if we didn't define bounds for our summation. Well, I mean, you understand what's happening here, right? I mean, it's really sum from 1 to n. You're breaking up your interval into n pieces, and so on and so on. That's what I mean here. And of course, for the integral, it's the integral from a to b on the interval you're working with. All right. Consider this. We already have y as a function of x. So it probably makes a lot of sense to try to set up our integral. We do kind of, Amir is asking if we get non-elementary integrals in this course. Well, we will discuss, right? I mean, what Amir is suggesting is we saw that this integral, or at least I mentioned that this integral does not have a simple closed form antiderivative. But this was still a very important integral, very much used in statistics and probability. And so, you know, the question is, how do we evaluate integrals using this? How do we evaluate this integral? How do we approximate this integral? And we're going to see that at the end of the course. This is what we're working up to. All right, so, you know, y as a function of x, we're going to go with this. We're going to go with this. And let's take the derivative, dy dx, which is 3 over 2 x plus 4 to the 1/2. And so your arc length which is the integral, in this case, from 0 to 4, square root of 1 plus dy dx. So 1 plus your derivative squared, right? I'm using this formula here. There it is. Square this. This is 9 over 4, x plus 4. Or 9 over 4x. Plus 10, is that correct? You know how to integrate. Simple U substitution does the trick. Can we do that in our heads? I'm sure we can. 2/3, 4 over 9. Everybody with us? And whatever that is. 8 over 27. 19 to the 3 over 2. And minus 10 to the 3 over 2. There it is. Same question. Ready with us? Questions? Is that the answer you got? Is delta x still b minus a over n in the summation? Sure, if you want. Yeah. Thank you, Paul. I mean, you don't have to give it an actual value, right? I mean, it's the idea of Riemann sum that's important. And if you have a summation f of xi star delta xi, if you can rewrite your sum in that form, then it's a Riemann sum. Can you find the arc length if the function is not continuous? You could split it up, right? I mean, if it has finitely many discontinuities, you could split it up, add those discontinuities. What do I mean by that? If you have something like this, you could find this length and that length, and then add the two together. Consider this example, where now you have x as a function of y. So it makes a lot of sense to use the second one. What about tan x on an open interval? A valid question, right? You're thinking about tan x, which goes to infinity here at pi over 2. But think about it, as opposed to the question of area, right? I mean, it is possible that the area here is finite. The arc length will not be, right? Because you're going to need an infinite piece of string to put it on your function. So the arc length is going to be infinite here. Right, so since x is written as a function of y, it makes sense to use the second formula. So let's find dx dy, which is y cubed over 2 minus 1 over 2y cubed. Is that correct? I'm sure you've had that already. Why don't we square it and add 1, just so we do the work here. Can you explain the relevance of the arc length and the integral which gives area? What do you mean here? We are asking two different questions, right? we're answering two different questions. One of them is the length of the curve. One of them is the area underneath the curve. I don't think there's necessarily any relation between the two. What do we have here? If you square this, you get y to the 6 over 4. This times 2, when you multiply them, the y cubes cancel. You have minus a quarter times 2 is minus a half. And then a 1 over 4 y to the 6. How do you get arc length? By finding an integral. Right, and that was the idea here. I suggested that we were going to approximate the arc length by a few straight lines. Right? So the arc length was going to be the sum of those straight lines, well, I mean, at least an approximation. And those straight lines could be viewed as a hypotenuse of a right angle triangle, where this is the change in x, right, because that's what it is, and this is the change in y. So this hypotenuse here was, by the Pythagorean theorem, this thing. So if you add all of these up, you get an approximation to the area underneath the graph, right? I mean, here you have another hypotenuse of a right angle triangle, and that is still delta x, and that is still delta y. I mean, different delta, so it's really delta xi, delta yi, right? And then we factored out a delta x or a delta y to get a Riemann sum. And once you have a Riemann sum, then the limit of the Riemann sum is the integral. That's the important thing. So that's why it was necessary for us to get a delta x outside or a delta y. As soon as you have that, it's a Riemann sum, and the limit is an integral. So that's the relationship between the two. And what I want to bring your attention to here is a typical trick that happens in these arc length questions. So you want to be on the lookout for it, but don't introduce it if it's not there. The 1 and the minus 1/2 cancel to give you just a plus 1/2. Right? 1 minus 1/2 is plus 1/2. And now this thing is the same as what it was originally. 1 cubed over 2 and 1 over 2y cubed squared, except plus instead of minus. Might not seem immediately clear by looking at this, but that always happens. If that does. So in this case, the arc length is the integral from 1 to 2. 1 plus dy dx dy squared dy, and we just work that out to be this business here, y cubed over 2 plus 1 over 2y cubed. Everybody still with us? Integration is trivial now. So that is 2 minus 1 over 16 minus 1 over 8 plus 1 over 4. Uh, 32, 33. 33 over 16. And as Michael suggests, arc length with respect to x or y should give you the same answer. The idea here, right, I mean, is that when 1 and minus 1/2 combine to give you a plus 1/2, then this whole thing is really the original thing that you had squared, but with a plus instead of a minus. Ashlyn is asking, why did we have the two equations set up equal to each other in the beginning? I am not sure what two equations you mean. Do you mean these two? I think that's what you mean. And then Michael answered, arc length with respect to x or y should give you the same answer. Do we have time for one more? Let's do one more. Let's try 16 here. Sophia is asking if it matters which direction we take the integral. In other words, 1 to 2 versus 2 to 1, it does matter. It does matter because if you're taking from 1 to 2, you're measuring this way, where the delta x is going to be positive. If you're doing it the other way, from 2 to 1, the delta x would be negative. And we have no way to account for that in the integral itself. So it should always be from smaller to bigger. So arc length again, 1 plus dy dx all squared. So in this particular case, what's the derivative of this? But if we just take the absolute value after evaluating, let's not do that. Let's not, because I mean, again, here you're taking an arc length, you're expecting a positive answer. So if you have a negative answer, you know something has gone wrong. In the same way that if you're evaluating the area, you're expecting a positive answer. If it's negative, something went wrong. Maybe it was just a question of bounds or something, but maybe it was a more subtle mistake, and you really need to go back and figure out what happened. The derivative of this, derivative of ln of cos, derivative of ln is 1 over. So 1 over cos times the derivative of the inside times negative sine. The whole thing is squared. In other words, 1 plus tangent squared, which you know to be secant squared. Square root of secant squared is, of course, absolute value of secant, but you know secant is positive in that domain. So no need for absolute value, it's just secant. You know the antiderivative of secant, right? Again, comes up so often. Secant of pi over 3, cosine of pi over 3 is 1/2, so this is going to be 2. Tangent of pi over 3, tangent is sine over cosine, sine of pi over 3 is root 3 over 2 divided by 1/2, that's just root 3. Secant of 0 is 1, tangent of 0 is 0, ln of 1 is 0, there it is. This one works out nicely, indeed it does. All right, there it is. How are we doing here? Questions? So practice this arc length idea. Next time, we're going to discuss surface area of solids of revolution. Do we need to state on a test why we can remove the absolute value sign directly? Should be pretty clear what you're doing. If you take the time to write this step, I think everybody's going to be happy. Well, I mean, it's a nice thing to do, to say that secant is positive in that interval. Yeah, might as well do it. So using arc length, knowing velocity, we can figure out the distance. Like if v is shown as a function, well, I mean, for the distance, do you need the arc length though? Right, I mean, if you talk about distance traveled, the use of arc length, I mean, it's certainly a very valid question, right? If you put, how long is this curve? If you put a string on that curve and you measure out the string, how long is it? That's the question we're asking. All right. Questions? let's say Sunday night at the latest for the midterm results. I hope. I'm going to put a bit of pressure on the TAs right after I log out of here. All right, so let me go do that. Thank you all for coming, folks. You guys have a good weekend, and I will see you on Tuesday, at which point we will discuss surface area. You guys have a good one.